Okay, let's get started. Are there any questions before we start? So last time we talked about the concept of a polar decomposition. Of course, well, we talked about the one-parameter subgroups and so on, but one of the things that we talked about was the concept of the polar decomposition, which is this theorem, which says that any matrix, maybe it's further down, sorry. Here it is. So the statement is that any matrix in GLNC can be expressed as a product of a unitary matrix and a positive matrix. A positive matrix means P equals P star, and its eigenvalues are positive real numbers. And then any positive matrix can be written as the exponential of a Hermitian matrix. So in other words, this theorem says that any element of GLNC can be written in a unique way as a unitary times the exponential of something Hermitian. Okay, and the u and the x continuously depend on a. All right, so that was the assertion. So now let's look at some examples of this decomposition in other Lie groups. So this theorem applies to elements of subgroups, Lie subgroups of GLNC, and that's what I want to do right now as an example. So say if we start with GLNR, so maybe I should write like examples of polar decomposition. So some examples. So if, say, you take an element of GLNR rather than GLNC, a matrix with real entries. So then we can, of course, write this polar decomposition U times P inside GLNC. But then what do we know about U? Pardon? It's in the orthogonal group, and why is that so? Yeah, but that's right. But more precisely, we have to think about the way we obtained U. So the way we obtained U was first we got P. P was the square root of A star A, and U was obtained as A P inverse. So when we think about it, if A is a real matrix, the square root of A star A will also be a real matrix. And therefore, the U will also be a real matrix. In other words, U will belong to the intersection of UN and GLNR. And UN is given by the condition, this is like matrices which satisfy this condition, but if they're supposed to be real matrices satisfying this condition, then the star will turn into transpose because the bar is not required. So you end up with the group ON. Oops. Let me see what happened with my colors here. Right, here's the thing. I should cancel this. Maybe this fixes it. Okay. All right, so I don't know how to remove that one now. It erases the stuff that's on the. But anyway, so the condition will be ON. Okay. And what about x? What is the condition on x? When we write p as the exponential e to the x, and we write p as e to the x, the condition that x is Hermitian will turn into x being symmetric. Okay. Maybe one more example. If we take an element of GLNC, I'm sorry, SLNR, then when we write A as UP, Well, what do we know about U and P? Well, just like before, U will satisfy this condition. It will be in G and R, but also that square root, everything will lie inside SL and R. In other words, this U will belong to UN intersect SL and R. So there's one extra condition on the determinant. So you end up with elements of SO and R, which means matrices such that X transpose is identity and the determinant of X is 1. Okay. And what about the X? So maybe I should, okay, I shouldn't use too many X's. So this should be, maybe I should just like U transpose U equals, because this is the U. Okay. And now P is the exponential of X. This time there's another condition on X, because the determinant of e to the X is supposed to be 1, because it's again coming from SL and R. What does it mean about X? It means that the trace is 0. So this X will be a symmetric matrix with trace 0. Okay, so it seems I probably did something to the zoom settings. Maybe I should first close the, okay, now if I reopen my OneNote, it might remove that green line, which was not moving. Okay, let me share again. Okay, now that's gone. Okay. Okay, any questions? All right. Now, another thing we talked about last time was the concept of a Lie algebra. Okay, so let's go further from the last lecture. So what is a Lie algebra? The Lie algebra is an algebraic structure, which is a vector space together with a bracket, which is bilinear and skew symmetric and satisfies the Jacobi identity. Okay, this mysterious identity, which I told you comes from properties of vector fields, basically. All right. And we saw some examples of Lie algebras last time, like R3 with a cross product, or the Lie algebra SLNR, SLNC, SLN over any field, matrices of trace 0 with the standard bracket, okay? The bracket xy minus yx. So in many of the examples of the Lie algebras, they're coming from associative algebras in the, equipped with the Lie bracket, which is the bracket xy minus yx, like you see here. Any associative algebra, so maybe I can add it on the next slide. All right. So maybe I should say more on the algebras. This is what we want to do now. So any associative algebra, unital or not, doesn't matter, equipped with this bracket xy equals xy minus yx, where the product is the product of the associative algebra, is a Lie algebra. Okay? All is good? All right? An associative algebra is just an algebra with a bilinear product which is associative. It satisfies the relation ABC equals ABC. Okay. All right, any questions? Now, given a, I mean, so, okay, what do we want to do with the algebras, or rather with algebraic objects from an algebraic point of view, not from a, like a more like a geometric point of view, which is in this course. When we have a bunch of algebraic objects, we want to understand sub-objects, and we want to understand morphisms in between them from a categorical point of view, right? So just do these things, the basics, with the Lie algebra. So first, what is a sub-algebra? So given a Lie algebra G, a subalgebra H of G. So a subalgebra of G is a subspace of G as a vector space. Maybe I should call it a subspace H of G with this Fraktur font. Which is equipped with the property that, I mean, equipped with the bracket of G with the property that the product of any two, or rather the Lie bracket of any two elements of the subspace belong to itself. Okay, so it's closed under this bracket, all right? And then H is a Lie algebra with this operation. And we can also talk about morphisms, homomorphisms between Lie algebras. So if G and H are Lie algebras, then a linear map like phi that goes from G to H is called a Lie algebra homomorphism if it preserves the bracket. So phi of xy equals phi x, phi y. And now if phi is a bijection, surjection and injection, then we call it an isomorphism. Okay, is everything good? Now, one of the most important examples of a Lie algebra homomorphism is, anybody has a suggestion? Anybody knows that? Those who have seen Lie algebras before? It's the adjoint homomorphism, so which I want to define right now. Okay. So let G be any Lie algebra. And now for X and G, we first define this map add X. This is a linear map from G to G. It's the endomorphism of the space G, defined as follows. Add X of Y is just the bracket of X and Y. Okay, so now, of course, add X is an endomorphism of G, so we obtain a map that goes from G into this vector space, or rather associative algebra, and G. They're like the linear maps on G. You can think about it as like a matrices with size dimension G. Okay, and now this map is a Lie algebra homomorphism. Let's verify that. And so which is called the adjoint homomorphism, the adjoint representation. I mean, so this requires a verification that we have a homomorphism. So that's basically like the subject of the next proposition, okay? So the proposition is that, so what should we verify? We should verify this add preserve the Lie bracket, right? But what is the Lie bracket of the endomorphism algebra of G? We think about it as an associative algebra and we induce it with the usual xy minus yx bracket, right? So if I take add of a bracket, it should be mapped to the bracket of the adds, right? But the bracket is inside NG. And as I said, this means add X, add Y, minus add Y, add X. So this is for all X and Y in G. Okay, so let's verify that this relation holds. So what's the left-hand side? Well, we have to evaluate it on some element. Like, so for any Z in G, left-hand side is X, Y, Z, like this. And the right-hand side, it's, well, you have to add X, add Y of Z first, which is X of Y of Z. Minus Y of X of Z, like this. All right. So now I would like to relate these two, and this is done using the Jacobi identity. So I first want to write it as a left aligned bracket. So I write the first one as minus Y, Z, X. And the second one, I can write this as well, I can just switch these two and these two, so I'll get ZXY. Okay, so I do two switch. Two switch, they don't change any sign. So now you see that equality left-hand side equal right-hand side is equivalent to the Jacobi identity. Because it will say that the sum of this and this without the sign and this without the sign is 0. Okay? Any questions? Is this clear? Everybody happy? All is good? Everybody following, hopefully? Yeah.
So why, at the very definition here, so is, why are we imposing that the curly bracket is a commutator? Are we imposing this or no?
I'm not imposing that. No, no, no. In the definition of a Lie bracket, it was only imposed that the bracket is preserved. I didn't say that the right-hand side or left-hand side are the commutator. Here, I didn't say anything. Right. But when I get the adjoint representation, well, I have to make end G a Lie algebra first. And the way that I make it is that I impose the usual, like the commutator of coming from the associative algebra structure. Okay, but this a priori is not a Lie algebra. I mean, why is it a Lie algebra? It's just an associative algebra, but it can be made into a Lie algebra.
So, and NG is NG going to be like the same as in the fact that like in your algebra with the matrix algebra? Is that isomorphism?
Right. So like, okay. So what is NG? So maybe I just have a recall. It's just the space of linear map going from G to G. So now you can of course, this is a vector space. You can add maps and like do linear combinations, but you can also compose them because they're going from G to G. And with this composition, it becomes this composition becomes the product of this guy as an associative algebra. So this is an associative algebra. So it's isomorphic to the matrix space MDC if I'm doing complex Lie algebras, where D is the dimension. G. I mean, I don't have to do this over C. I can do this over any field. Let me first be sort of more precise about that.
Right.
Now, what's the question?
Is it always going to be a central simple algebra?
I don't know about positive characteristic, but yeah, I mean, characteristic 0, it's a simple symbol. I mean, this is just a very simple central simple algebra. Yeah. It's even a simple algebra. I mean, yeah. Yeah. Now, one thing I wanted to say, and I forgot, is that when we talk about Lie algebras, we can consider them as vector spaces over arbitrary fields. Like this is like, I mean, in this course, the fields are just R and C because we're doing Lie groups. But we can still think about Lie algebras over R or C. And when we think about a homomorphism of Lie algebras, the two Lie algebras should be on the same field. Occasionally, we might consider a real subspace of a complex vector space, and rather more precisely, a real Lie subalgebra of a complex Lie algebra. But any complex Lie algebra is also real Lie algebra because it's a real vector space as well. Any complex vector space is also a real vector space, but not the other way around. Okay, so sometimes we talk about complex Lie algebras, and sometimes we talk about real Lie algebras, and sometimes we also talk about complex Lie groups and real Lie groups. We will make that distinction, what we mean by complex Lie group, a bit later. Okay. Any questions? Now, another thing you can do with Lie algebras is we could do some kind of, okay, in categorical language, you want a coproduct maybe, or rather you could just construct new Lie algebras from two other Lie algebras. So here is the definition. The given two Lie algebras G1 and G2, their direct sum is the Lie algebra with an underlying vector space G1 direct sum G2. So we just take the direct sum of the two vector spaces and a bracket, which is obtained from the sort of component-wise bracket. So the bracket of x1 plus x2, y1 plus y2 is defined to be x1, y1 plus x2, y2. This is for x1, y1 in G1 and x2, y2 in G2. Okay. Now, in fact, G1 and G2 are going to be ideals of this direct sum, which I'm going to define. So maybe, so here's a remark. In fact, G1 and G2 are ideals of G1 plus G2. And in fact, they commute. What does an ideal mean? A subalgebra H of a Lie algebra G is called an ideal if not only it's closed under the bracket, but when you take the commutator with elements of G, you end up in H. Well, this is just an inclusion, not equality. Okay, so this relation means any X in G, any Y in H, the bracket will lie in H. And when you have an ideal, just like you have an associative algebra, so I will not explain all of this, but these are like, we are not going to need this much, but anyway, it's useful to know. So we can always, so for an ideal, we can construct a quotient. Okay, but we don't need this. I mean, it's just like for those who know how to construct quotient, you can construct the quotient of this guy too. And you don't know what the quotient to construct, don't worry about it. We don't need it much. I mean, we basically don't need it. Now, another important thing in the theory of Lie algebras is the concept of a structural constants. If you take a Lie algebra, how do you recognize the structure of this Lie algebra? What are the ways to understand what's going on in there? So what you can do is you can choose a basis and then write the brackets of the basis elements in terms of the basis. Then you get a bunch of numbers, and these numbers technically describe this Lie algebra of isomorphism, right? And these are called the structural constants, okay? So it's good to know what they mean. So let G be I mean, for simplicity, let's assume it's finite dimensional. Let's say it's over R or C, doesn't matter, or any field. And now let x1 to xn be a basis of G over that field. Then we can express brackets as xi, xj is sigma Cijk, k from 1 to n, xk. Okay? Where the Cijk's are in R or C, respectively, whatever the field is chosen. Okay? And the Cijk are usually called the structural constants. And they satisfy some natural relations. The skew symmetry of this list of the Lie bracket, it imposes the following condition: Cijk plus Cjik equals 0 for all ijk. And the Jacobi identity imposes something a little bit more complicated. Sigma Cijn Cnkm plus Cjkn Cnim plus Ckin Cnjm is 0 for n. Okay, bad notation, I guess. Maybe instead of n, I should have used L. Because I had an n already, so Cijl, Lkm, Jkl, Lkm, Lim, sorry. Kil, Ljm is 0. This is for all L from 1 to n. So this is for all I, j, and k indices, and this is for all I, j, k, m. Yeah. So as you see, I didn't remember even this formula. I have to check my notes, and that's just because this formula is not extremely useful. Okay. Occasionally, you might take advantage of structural constants, but not necessarily these explicit relations, right? Okay, so now when we start studying some subject in algebra, we should start understanding the simplest objects there. Okay, so then let's define what a simple algebra, what a simple Lie algebra is, and try to characterize them. Okay, so here's the definition. What is a simple Lie algebra? What should it be? What should the definition be? So yeah. That's right. So the algebra G is called simple, just like when you define a simple ring. Well, there is an extra condition. I'll tell you why it is there. So the condition is if the dimension of G is bigger than 1 and does not have any proper ideals, and G does not have any ideals other than the trivial ones, which are 0 and G. So you exclude the abelian one-dimensional algebra because that would fit this definition of not having proper ideals, but that we don't want to call simple for many, many reasons. It will just make a nice classification ugly. Maybe that's I can explain. Basically, in all papers on simple Lie algebras and simple Lie groups should have said if G is a simple Lie algebra other than the one-dimensional. So just to save some ink and paper, we exclude this guy. Okay, so now can you give an example of a simple Lie algebra then? Does anybody know an example of a simple Lie algebra? That's right. So I'll get there, but let's just start with a simpler version of even SL2. So SL2C. I didn't hear if you said SL2 or SL3. Okay. All right. SL2 is a simple Lie algebra. So let's prove that this Lie algebra is simple. And this proof is important because it says something about the structure of this Lie algebra, which is one of the most important facts in representation theory. And that is the existence of this nice SL2 triple, this nice basis. So SL2C has this basis like H, which is the diagonal matrices with trace 0. Here I use E and F, yeah, E, which is the matrix 0, 1, 0, 0, and F, which is the number 0, 0, 1, 0. So these three matrices, like they span, they form a basis for SL2C, right? And now the commutator relations between them are easy to describe. You can see that EF is going to be H. It's just a matrix commutator of this, like E times F minus F times E, like as matrices, right? So maybe I just write it like EF minus FE. You can do the calculation and you see that you get H. And now what about HE? When you do this calculation, HE minus EH, you end up with 2E. And HF, can you guess what you get? Those here are online. Any suggestion? It's a matrix calculation. Can you do it in your head? Minus 2A, minus 2F. Yeah. Okay. So these relations, basically anybody who wants to do Lie theory should know these. These relations, I mean, you should know them by heart. I mean, you do know them by heart. You use them so often that you basically know them by heart. So now, how can we use this to show that this Lie algebra is simple? Suppose it has a H is an ideal of SL2C, not equal to 0 is an ideal. I'm going to show that H is in fact the entire SL2C. So let's take some element there. So take some element in H, non-zero. Then how can I express this element? Then this element is of the form AE plus BF plus CH for complex numbers ABC. 'C. Okay. So now what can I do? So now what can I do? Then this element is of the form AE plus BF plus CH for complex numbers ABC. Okay. So now what can I do? 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 So now what can I can take the bracket with H, right? So let's do HZ. From the above formulas, I can just write this out and see that I get 2AE minus 2BF. I don't have the H guy because HE will produce only E and HF will only produce F, and HH is just 0. Okay, maybe I should have added here, so HH is 0. Okay, it's diagonal, okay? And now, well, what I know is that this is like we have an ideal, so this should be in H. And I can do the bracket one more time. Still, I should get an element of H. But this time I'm going to get 4AE plus 4BF. And that should still be in H because I have an ideal, okay? So now what does it mean? If A is non-zero and B is non-zero, then what can I do?
You can have plus, and then add the second line you'll get.
That's right. So the first one basically says E minus F is in H. Then the second one also says E plus F is in H. And from these two, it follows that E and F are in H. Just do the linear combination of these guys. And finally, H, this capital H, which is the commutator of E and F, is in H. And this means that H equals SL2C. Oops. All right, so if the coefficients A and B are non-zero, then in fact, you do not have a proper subalgebra, proper ideal, okay? Oops, what happened? Ah, did I lose it? All right, sorry. I'll just start it again. Ah, okay, so now I see what happened. Okay, and now what if the coefficients are zeros? For example, if A is 0, well, as a consequence, well, we know that this Z is non-zero. Well, okay, we could just argue a bit like, okay, we could just continue. In many ways, we could argue. So then what do we know? Then like Z is BF plus CH. And this time, you could look at like ZF and, or rather FZ. So here I did, yeah, it doesn't matter. So what do I get as ZF? So I get this FF, which is 0. And then I have this C times HF, which I get minus 2 CF. Okay. And again, if C is non-zero, then what we have is like F belongs to H. Hence, H itself, which is EF, is also in H. Hence, E, which is EH, or HE, I don't know, divided by 2, is in H. And again, we have proof that H equals SL2C. Okay, and finally, if A is 0 and also C is 0, then, well, Z is like BF, where B is non-zero. And I mean, this time again, you can just take the commutators with E. Right? So again, we get this L2C. Right? So the proof is not difficult. It's just by some, I mean, algebraic manipulation, like case by case. But it's kind of, it becomes more difficult if you want to think about the more general assertion, which I give here in this example. The Lie algebras SLN-R and
May
SLN-C
I ask a dumb question?
for arbitrary n at least 2 are simple. Okay, so this can be proved by a more lengthy calculation based on this technique, but also by more conceptual and smarter ways. That they're simple Lie algebras. What about GLNC? Do you think it's simple? GLNC is not simple. What is, like, what are the ideas of GLNC? The center is an ideal, and SLNC is also an ideal. Okay, so GLNC is isomorphic to the direct sum of SLNC and the one-dimensional Lie algebra. What about the orthogonal guys? What about SONC? So what is this SONC? This is supposed to be the Lie algebra corresponding to that Lie group SONC, right? And so to be more explicit, this is the set of matrices in, I don't know, in SLNC, GLNC, doesn't matter, such that X plus X transpose equals 0. Skew symmetric matrices with the matrix commutator. So you can check that this is a Lie algebra. Because the commutator of two skew symmetric matrices remains a skew symmetric. Xy minus Yx for X and Y skew symmetric is still a skew symmetric. You just take the transpose, you just, use properties of transpose. That's elementary. But is it simple or not? What do you think? So let's write some examples. What happens for n equals 2, which is the smallest interesting example? So SO2C is the set of matrices of which form? 0A minus A0. What Lie algebra is this? What's the dimension?
Dimension.
It's dimension 1, so it's really isomorphic to C. Okay, so this is we didn't call it simple. All right. What about SO3C? We did something in class related to this. What did we do? We proved some kind of Lie group version of this. So remember in class we proved that SU2, there's a homomorphism from SU2 to SO3R with the kernel which is only plus minus 1. Okay, there's an almost bijection between the two. It will turn out that there is actually an isomorphism between the Lie algebras, the Lie algebra SU2C and the Lie algebra SO3R. And if you complexify this story, you will see that this is isomorphic to SL2R, SL2C, I'm sorry. So it's simple. All right. So this is like n equals 3. Maybe I just write n equals 3. What about n equals 4? Does anybody know what happens? SO4C. What's the story here? Is it simple? Is it not? It's one of those famous exceptional isomorphisms. It's isomorphic to SL2C, direct sum SL2C. And I'll tell you why shortly. So it's not simple. It's got like an ideal, right? Like. So now what happens for n equals 5 or higher? It is simple. That's right. Okay, and now let me tell you why for n equal 4 it's not simple. It's just a matter of finding some isomorphism. So the case n equals 4. Let me explain this. Why is it that it's SL2C plus SL2C? Well, we need to, in order to see this easily, we need to think about SO and C in a slightly different way with a different matrix. So remember this SONC, this group, it was the set of matrices that would preserve some, like they were isometries of some symmetric bilinear form, right? Now you can choose a form which is diagonal. In other words, the matrix of the form is just the identity matrix, but you can choose any symmetric matrix and write this bilinear form. Any symmetric matrix with determinant 1, it will correspond to a symmetric bilinear form just by taking, if you take any such matrix, you take X transpose AX as, or rather X transpose AY as your bilinear form in X and Y. Okay? And the isometries of this bilinear form should be a group isomorphic to SO and C. Okay? Just because any two such forms are conjugate by some matrix, so in fact, you can conjugate that group to this SO and C. That's right. So we determined 1. That's right. I'm sorry. So if what I said, I should say like isometries would be O and C. Okay, maybe yeah, you're right. So I should use O and C, and it doesn't matter which matrix I use. Yeah, you're right. Okay. And to get that SO, you take the isometries with determinant 1. Okay. Volume preserving isometries. Maybe the canonical, the kind of conceptual description would be volume preserving isometries. Volume and orientation preserving, I'd say. Actually, the volume is wrong. Sorry, I should say just orientation preserving. Volume would be if I do GLN versus orientation preserving. Sorry. Okay. Maybe I should say, so SO and C would be orientation preserving. Strictly speaking, I wasn't wrong, but I was redundant. Okay. Volume can go to minus the volume. Anyway, so now same thing holds for the Lie algebra. So instead of thinking of matrices, or rather describing the matrices in such a way, you could get a slightly different description for any symmetric matrix, in particular for this matrix. So if J is this matrix 0, 0, 1, 0, 0, 0, 0, 1. No, I don't want that. Sorry. So J is this anti-diagonal matrix 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. So then SO4 is isomorphic to the set of matrices of size 4 by 4 such that xj plus j transpose x, well, jx transpose, I'm sorry, I got carried away, jx transpose is 0. If I said j equals I get that previous description. But I could use this J or any other invertible symmetric matrix. And the Lie algebra that I get and the other one are just the same. Up to, like there's an isomorphism between the two, which is by matrix conjugation. Just like the assignment problem. The problem about SU11 versus SL2R. Okay? So now, with this form, when you just write out what this means for a matrix to satisfy this relation, you can actually see an explicit form of the matrix. So it follows that. What time is it? Okay, we still have time. Okay. Elements of SO4C are 4x4 matrices of the form they're in this block form like this, where here you have X 0A minus A0, 0B minus B0, and minus X transpose, where X is just an arbitrary 2x2 matrix. Okay. Where A and B are just complex numbers. This will be the matrix description when you do the calculations from here. Just do the matrix multiplication and see what you get. Okay. And I encourage you to do this exercise to understand what's going on in this example, and also in similar examples. All right. So now I want to see two copies of SL2 here that commute with each other. So one copy I basically get on the diagonal. Okay. So now the set of matrices of the form x0, 0 minus x transpose with trace of x equal to 0 is isomorphic to SL2 as a subalgebra of SO4. And now where's the other guy? Well, I have not used the diagonal here. And those two other positions which have like the A's and the B's. So now I can take H to be this matrix, 1, 1, minus 1, minus 1. It is the diagonal part of the sort of the X on the blocks. And I can take E to be this matrix. So it's like A is 1, B is 0. So I get 0, 0, 0, 0, 1, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is for the case A equals 1, B equals 0. And I can take F equals, just this time B is 1A 0. So I get a 0, 1, minus 1, 0, 0, 0, 0, 0, 0. Okay, so I have these three matrices which are contained in SO4C with this realization. And those three matrices also span an SL2C. And it's not difficult to see that this SL2C and the other SL2C, they commute. So they need these E, F, H also span another copy of SL2C in SO4C, and the two copies commute. So this means that the bracket of elements, one from this copy, the other from the other copy, is always 0. So this means that because the sum of the two copies is all of SO4C, in fact, each of these copies is an ideal. And so you have described your SO4C as a direct sum of these two ideals. Okay? Any questions? All is good? Everybody happy? Okay, but that is just an exceptional situation. It only happens for n equals 4. For other n, you cannot have such a decomposition. As we know, the algebra is simple. Okay? Okay, so now let's move on and talk a little bit about other types of Lie algebras, like with other properties, okay? Oops. Okay. So the first, okay, so or rather, okay, the first type of Lie algebra that I want to talk about is the solvable Lie algebras, and this is similar to the solvable groups that many of you studied in your algebra course, maybe last semester with me or with like recently with someone else. Okay, so what is a solvable Lie algebra? Well, what's a solvable group? Does anybody remember what a solvable group is?
The derived series.
That's right, the derived series terminus. So first we have to define the derived series. So in the Lie algebra case, so if G is a Lie algebra, the derived subalgebra, or rather the commutator of subalgebra or commutator ideal, it happens to be an ideal, is GG, noted like this, which is defined to be the span over the base field of all brackets of the form xy with x and y and g. So you take all commutators, and well, they might not form a subalgebra themselves, but you take their linear combination, it will form a subalgebra. In fact, it will be an ideal, clearly. Okay? It's just an ideal by definition. This is like an elementary, very, very simple exercise to see this as an ideal. And now you can keep taking the derived, or rather the commutator ideal of a Lie algebra successively. And if you get to 0, your initial Lie algebra is called solvable. Okay? So here's the next definition. So for any Lie algebra G, we define a sequence of subalgebras like G equals G0, G1, G2, and so on. In fact, maybe I should just put the inclusion relations here. Where each GI, or rather each GI plus 1, is the commutator of the commutator ideal of the previous guy. In fact, each GI will also be an ideal of the big Lie algebra G. And now this sequence is called the derived series of G, and we say G is solvable if GI is 0 for some I. So whenever we have an exotic definition, it's good to think about examples of that definition. So can you give an example of a Lie algebra which is solvable, other than the trivial Lie algebra?
Well, maybe a one-dimensional algebra because they're a billion.
Okay, but maybe a more non-trivial example? Yes? The strictly upper triangular, or even just the triangular ones, right? So you take G to be the Lie algebra of matrices, which are 0 below the diagonal and arbitrary on the diagonal. I mean, like, these elements are in C, so this is like the upper triangular matrices. With the usual bracket. xy minus yx. So maybe I should say as a subalgebra of GL and C is solvable. Any subalgebra of a solvable algebra is also solvable because the derived series will be included in the derived series of the one that's bigger. But that bigger one has a derived series that terminates, so the smaller one will have the same property. Okay, so any subalgebra, any Lie subalgebra of this G will also be like the diagonal or the strictly upper triangular, as it was mentioned, right? And now let's give an example of one which is not solvable, which we talked about today, like SL2. What is the commutator? When is the commutator ideal of SL2C?
It should be the whole thing. Didn't we show this the whole thing?
Why is it the whole thing?
Because by regarding it.
That's right. This commutator should be an ideal. There are no proper ideals, so it can only be 0 or everything. But can it be 0? No, because SL2C is not abelian. SL2C, that there are like matrices which do not commute with each other. So it can't be 0, so it should be everything. So hence the derived series is non-zero constant. I mean, but I mean, my constant is like, it's just this SL2C, it just keeps being SL2C all the time. Is it good? Everybody happy so far? Everybody following? Everybody excited? Hopefully. Not so much? Yeah.
Are there a lot of solvable algebras?
Yeah, there are exotic examples. That's true. There's certainly more than simple algebras, let's say, because simple algebras are classified. There are just 4 families and a bunch of exceptionals. But yeah, solvable algebras, there is no classification. There can be exotic features, right? Okay. Now, yet another class, which is like with a more strict condition than being solvable, is the class of nilpotent algebra. So let's talk a little bit about that. So for any Lie algebra G, this time we define something that is called a lower central series of G. So this is now a sequence of ideals starting from G So what is each GI? Each GI is the commutator of G with the previous GI, or rather like GI plus 1 is GGI, or rather this is like the notation. So this really means the span of brackets XY, where X in G and Y is in GI. So again, you can check that each GI is an ideal. It's a fairly elementary exercise using the Jacobi identity, I guess. Yeah. And we say, so we call this sequence the lower central series. And we say G is nilpotent if G. So I did a bad thing. So I think I should have changed my notation. So here the indices, maybe I should write them above, just because for the lower for the derived series, I wrote them below. The G0, G1, Gn. So this Gi plus 1 is GGI. Okay. Oops. Okay, so we say G is nilpotent if Gi is 0 for some I. So if this sequence terminates in 0 at some point, then we say G is nilpotent. Now, here is an important, here is a sort of a remark. The book calls this the upper central series, but I checked in many places, and in fact, this is the lower central series. So I first noticed that, this is supposed to be called the lower central series. So I thought, okay, maybe there's discrepancy about the terminology. And then I went online and I realized wherever I looked, it was called the lower central series. So there is a sort of a small error in the book, in this book. Okay. Now, why is it deserves to be called the lower, but not the upper central series? Why do we call it the lower central series?
So in group theory, you have an inclusion. This is under.
Right. This is, so there's another central series, or maybe one can define a family of central series in general, actually. And this one is included in all of them. Okay. So what is the one that's called the upper central series? I'll just briefly mention it. We don't really need this. What is the upper central series? You start with the center of the Lie algebra, which is the sort of all elements. I didn't define this even. The elements that commute with the element of G. And now you should take this quotient. So this is maybe called, I don't know, there's like a G0. And you look at this quotient, and you look at the center of this one, and by the quotient construction, this is like some G1 over G0. And then you repeat this. Then you just form like G over G1, and you form the center, and da da da. This is why you get a sequence of the algebras that go up. They're kind of trending upwards rather than the one that I showed you, which are kind of going downwards in size. And this guy is called the upper central series. But anyway, this is just a digression. You don't need to know what it is. Now, let's do some examples of nilpotent Lie algebras. The strictly upper triangular matrices is a nilpotent Lie algebra. That's because each time you take the commutator of some strictly upper triangular and something in the previous ideal, the level of triangulation goes up. So I mean, in the beginning, you have zeros on the diagonal, but arbitrary things in here. But if you take the commutator of two things of this form, you get a matrix which is a 0 here, and it has a row of zeros, like an inclined diagonal of zeros above it. And now if you take the commutator of this guy with this guy, your level of zeros goes one level up. And it keeps going up and up and up, and eventually it will kill everything. Okay, so it's very simple. But the upper triangular matrices, they do not form a nilpotent Lie algebra. Because when you take the commutator of a triangular and a strictly upper triangular, you remain in the strictly upper triangular. You do not get one extra row of zeros. Okay? So, however, the Lie algebra of upper triangular matrices for n at least 2 is solvable but not nilpotent. How are we doing with time? Okay, everybody happy? Everything is okay so far? No questions? Yes.
Like algebra, nilpotent matrices,
The subalgebra, Lie subalgebra of nilpotent matrices. This is a great question. This is closely related to Lie's theorem in Lie theory. There's a theorem called Lie's theorem. Lie's first theorem. I mean, yeah, first theorem and second theorem. So, well, okay, there's Lie's theorem and there's Engel's theorem. So I think a Lie subalgebra of nilpotent matrices. I mean, I think it is true. Yeah, I think it is true as a consequence of Engel's theorem. We have to check that a Lie subalgebra of nilpotent matrices can always be upper triangularized. It can be turned into, like, they can be simultaneously triangularized. The question is, you see, this is like a standard thing in linear algebra. You have a bunch of matrices. When can you triangularize them at the same time? And if you have a family of matrices that commute, you can triangularize them simultaneously. But I think it's also true that if you have a family of matrices which are all nilpotent and they form a Lie algebra, then you can triangularize them simultaneously, and therefore they're all strictly upper triangular in this change of basis. But prior to that, you can't assume that. I mean, even for like one-dimensional, you can have a nilpotent which is not triangular, not upper triangular, okay? Did I answer your question? Any other questions? So here is a definition, and we will continue next time on this definition. How much time we have? Okay, not much time. So, okay, we studied quite a bit of Lie algebras. Now we want to relate Lie algebra theory to Lie group theory. So let G be a matrix Lie group. Okay, so this means a closed with respect to topology of the subgroup of the LNC. Okay. So now the Lie algebra of G. So we want to define the Lie algebra of G, which we keep, like it's pretty standard. If you have capital G as your group, you'd use this German G, fracture G, as your Lie algebra. Okay. You try to kind of stay consistent with this choice of notation. Okay. The Lie algebra of G denoted by G is defined as follows. So it's the set of matrices in M and C such that for every T in R, the value of the one parameter subgroup generated by this element lies completely inside G. Okay. So all X's in M and C such that the one parameter subgroup generated by them will lie inside the Lie group G. They form a Lie algebra. We will show that they will form a Lie algebra, and this Lie algebra, of course, deserves to be called the Lie algebra of the group G. And more or less, the structure of G is understood by this Lie algebra. A lot of things about the structure theory of capital G can be understood using little g. Okay, so here just I finish by this remark that for X in G, in this Lie algebra defined as follows, maybe just like let's write Lie of G. This is another notation commonly used. So we have e to the x is in the connected component of identity of G. That's just because this is a path connecting the identity element to e to the tx. So it should lie in some path connected component of the should lie in the path connected component of identity. In other words, the concept of the Lie algebra only sees the connected component of identity. G and G naught, they will have the same Lie algebra. So this concept cannot distinguish between disconnected Lie groups, but for connected Lie groups, it more or less contains the structure. As like Lie's third theorem, which we will prove later on, much later in the course, shows every for every such for every Lie algebra, there's a unique Lie group simply connected associated to it up to isomorphism. Okay, I guess we can stop now. Next time, I'll prove that this guy is actually Lie algebra. I haven't proved it yet. And then we will look at a lot of examples and properties of this Lie algebra. And where are we going then? After this, I think we're going to basically try to like define the exponential map of a Lie group and understand the Baker-Camper-Hausdorff formula, a lot of other things. Okay.